Hi, everyone. Good? Hi everyone, and I'd like to thank the organizers for this wonderful summer school. So I will start these lectures with this PDF file, which will be completely an impressionistic view of what we will prove. So for alpha now, it won't be rigorous. It won't, just to give you a little bit the flavor of what will follow. And then I'll use this really nice blackboard, and we'll start from scratch, and hopefully it will be rigorous and understandable for everyone. Okay, so for the next alpha now, you don't need to take notes or anything. So the title is Noise Sensitivity and Percolation, a notion which will be very central in this lecture's notes is the notion of a Boolean function. So you probably all know what it is, but at least for the notations I'll recall here. So a Boolean function for us in this course will be a function from the hypercube -1, 1 to the n, which will take two values, either 0 and 1 or -1 and 1, depending on the context. So I just give one example here, the majority function. So if you take n bits plus or -1, the majority will be 1 if you have more pluses than minuses, and -1 if you have more minuses. If you want this to be maybe well defined, maybe n should be taken to be odd. So in this course, we'll see many other examples of Boolean function, and somehow the first part of the course will study Boolean functions in general, and then we'll apply these things to percolation and things like this. So Boolean function, as you know, they're very central in computer science. And since quite a long time, people in computer science, they provided many results, many theorems about Boolean functions. And in the first lectures, we will explain and prove some of these results, because the techniques that they invented to study Boolean functions will turn out to be very useful in our later applications to percolation. So we'll have some insights about Boolean function from the computer science community. Another source of insight will be probability, namely the bits, the random strings, the string of bits, the input of the Boolean function. Often it will be very useful to think of it as a random strings of bits, and therefore many useful tools from probability will be helpful here. Another thing which will be which we will use through the whole course will be discrete Fourier analysis. So many times in this course we will decompose a Boolean function into Fourier series, and in some sense the spectrum of the Boolean function will contain a lot of information relevant for us. So these three things which surround Boolean functions, they are very well known for a long time, and since we give this lecture in a summer school about probability and statistical physics, the main goal is to use all of that and so that we can prove some phenomenon, and I hope some surprising phenomenon for you in the context of statistical physics, and in particular for the model of percolation. So before moving to the general study of Boolean function and in particular in the context of percolation, I'd like just for 5 minutes to give you a very concrete situation. I won't come back to it later, but it gives maybe a picture of some of the notions we will use. The case of voting schemes. So imagine you have n people which are deciding between two candidates, and they decide together for a certain procedure or a certain voting scheme, and this can be exactly represented by a Boolean function. Right? Each choice of the n people is -1 or +1, depending whether they want candidate A or candidate B. So the first example I gave in these slides, majority, would be one example of a voting scheme. You could also think, for example, of this other situation where A would be Al Gore, B Bush, The number of people I didn't check, but I guess roughly 100 million. And the Boolean function here would be a bit more complicated because it would be a kind of iterative majority. So why do I introduce this concrete situation? Because it enables to explain the notion of noise stability. So remember the title of the course is noise sensitivity, but somehow this is the other extreme. So when you have an election, suppose you know that the election is well balanced. Say polls are saying that the election is well balanced. I don't know. So you may consider the actual string of choices as a random string of bits sampled according to the uniform measure on the IMPA cube. So the outcome of your election ideally should be the value of the Boolean function on this string of bits omega. But of course, if you have 100 million people voting, inevitable errors will occur, and the actual outcome of the election will be f of omega epsilon. And omega epsilon, you should think of it as a slight perturbation of omega. And so this omega epsilon will come over again and again in the course. I will define it properly once on the blackboard. But somehow you may think of it as you have your n bits, and you change each bit with a very small probability epsilon. So somehow omega epsilon will be almost identical to omega up to a small proportion epsilon of the bits. So, of course, in the case of voting schemes, you'd like that the actual outcome would be the same as the outcome that people really decided. So you'd like the probability that f of omega is different from f of omega epsilon to be as small as possible. And informally speaking, noise stability for Boolean functions will correspond to this quantity being close to 0. So I'll come back to this later. So just if we consider the first example I gave, which is one of the examples of voting schemes, when you take majority, if you consider your votes as ID votes, sampled according to the uniform measure, if you order your voter linearly like that, majority is exactly related to simple random walk, and you just look at the sign of your random walk at time n. So now if you noise your random walk a little bit, namely that you only change a small proportion of the bits, it's not hard to convince yourself that somehow the picture will be very stable. So you could estimate what would be the probability that there is a change, but this will go to 0 when epsilon will go to 0. So there are many deep theorems in computer science which, under certain hypotheses, show that the majority function is the most stable Boolean function you may dream of. So this, I won't come back to it. So now we see that random walks are objects which are very stable when you perturb them a little bit. If you would go to the continuous, like in Jean-François's course, somehow everything which comes from stochastic calculus in a nice way would also be stable on the slight perturbations. And the purpose of this course will be to move to a statistical physics picture in the case of percolation, and to ask how percolation will react when we noise it a little bit. So let me recall very quickly some of the things Vincent mentioned in his course yesterday. So if you take percolation on DD or here on D2, you have a subcritical regime below p equals 1/2, where all the clusters, when you rescale the picture from further and further away, the cluster will look smaller and smaller. And Vincent gave quantitative statement for that. In some sense, they're logarithmically small. Similarly, in the subcritical phase, you'll see an infinite cluster going more or less all over the place. And when you rescale the picture, there is no geometry remaining. So for us in this course, we'll only stick to the critical picture, where you know that there is a lot of nice geometry. You have the SLEs at the scaling limit if you are on the triangular lattice, things like that. And the questions we will ask, it's a little bit like with this random walk here. What happens for critical percolation when you perturb it a little bit? So what do I mean by a perturbation? Say here you have a configuration of critical percolation on the hexagonal lattice. A perturbation from omega to omega epsilon, well, you change a small proportion of the bits like that. So the question is, how does critical percolation react to perturbation? Let's look at macroscopic structures at big connected components, and let's see how they behave. So this is the picture which is on the beginning of the lecture note, but since it's black and white, I'm not sure it works very well. So here so let me explain. So this is a critical percolation in Z2 on a window, I don't remember very well, but maybe 100 by 100. And these three clusters are the three biggest clusters in terms of cardinality. And from left to right, we applied some small amount of noise, which I don't remember as well, but if you would look from closely, you would see that the configuration didn't change so much. And somehow, the purpose of one of the main purposes of this course will be to prove that the geometry at large scales is very sensitive when you perturb a little bit the bit. So why did I start with Boolean functions? And this doesn't seem to be so related to Boolean functions stated like that. So now you have many natural Boolean functions in this picture of critical percolation. And in some sense, they encode everything you want to know about macroscopic properties. So for example, here is one class of Boolean functions that we will consider very often. Take a large rectangle. So this is exactly the same rectangle as what Vincent drawn yesterday for the Ttl theorem. And look at the Boolean function whose inputs are all the edges in this picture. So you have about constant time n squared bits involved. And your Boolean function will be said to be 1 if there is an open path from left to right, and 0 else. So this is the same thing as what Vincent said, but in the context of Boolean functions. And by Ritz-Welch, we know that this Boolean function is has a variance which is bounded away from 0. Or if you prefer, this is a Boolean function which is well balanced. So positive fraction of the time it takes value 1, and on a positive part of the hypercube it takes value 0. So I gave an informal definition about noise stability. Now let me give an informal definition for noise sensitivity. How to make sense of the fact that this picture is very noise sensitive? This will be related to proving that asymptotically, when you take larger and larger boxes, these Boolean function from omega to omega epsilon, they will decorrelate very quickly. So to quantify a little bit, being a Boolean function, if you want a Boolean function to be noise sensitive, you want that Fn of omega and Fn of omega epsilon are very little correlated, or in other words, you want that the covariance is very small. So again, I'll come back to a precise definition later. And our goal will be to prove that such things will be indeed noise sensitive. So this is already interesting in itself, since you see that the picture is very chaotic when you change it a little bit. But we'll apply it to the model of dynamical percolation, which is basically like doing Glauber dynamics for Ising model, but in the case of percolation. So this is a very simple model which is a Markov chain on the configuration of percolation, and which is stationary. And a way to define it, but we'll come back to it in the later in the course. It's that each site or each edge will switch its color according to a Poisson-Point process. So maybe just so that you picture a little bit what's going on, here is a movie done by Odette Schramm. So imagine you have the infinite plane, and you have a critical percolation on the triangular lattice. And each hexagon flips its status according to Poisson-Cohn process. So imagine this is moving in the whole plane. So at each time, if you stop this dynamics, you see exactly something sampled according to critical percolation. And now you may wonder, is it the case that the properties of the movie are different from the properties of the static picture or not? So for example, as Vincent explained yesterday, at the critical point, we know that almost surely there is no infinite cluster. Well, that doesn't imply that if you look at the movie, you might have exceptional times where there is some explosion, an infinite cluster might appear. So one of the big questions we'll face in this course is trying to prove the following theorem, that indeed you have you have times where there is explosion and you have infinite clusters which appear in this movie. So it's hard to draw, but Vincent, we asked Vincent to make this movie, and I think it illustrates well. I don't know if you see very well. It's a bit unfortunate, but wait. So here you have a critical percolation in Z2, and in red, the connected component at the origin is colored in red. Can you see? Or? So now I'll do the same movie as behind, but we'll follow how the cluster at the origin moves in time. So before I show you the movie, it's pretty clear that if the cluster at the origin is very large, it will interact with many people, so it should move faster than when it is very small. So now let's see what it leads to. So somehow at large scales, things are very chaotic, and well, you might be convinced that, yes, it seems plausible that we'll have explosion times. Okay, so thanks, Vincent, for the movie. Yeah, so why is noise sensitivity related to trying to prove that explosion times exist? If you take this model of dynamical percolation and you look at the configuration at time t in a very large window of size n, and you look at it at a time slightly after t plus epsilon, omega t plus epsilon is exactly an epsilon noised version of the omega t, as I explained before. And noise sensitivity means that somehow all the large-scale properties has been completely mixed. It completely forgot its past, and somehow the system at large scales is moving very quickly. So maybe intuitively, if you have such a system which in small interval of time visits many different configurations at large scales, it will have more chances to try to visit further and further away. So the very heuristics of the proof of existence of exceptional times is first to focus on the question of noise sensitivity of percolation. So I hope this motivates this question. I'll give very quickly an application of a somewhat different flavor in the context of first passage percolation. So here, very informally as well, again, what you do is you take the graph ZD. So here we don't need to be two-dimensional. And you define a random metric on ZD as follows. For each edge, you choose its length to be some parameter E with probability 1/2, or some other parameter B with probability 1/2. So you end up with ZD and with this random metric. And you might wonder what are the properties of this random metric. So for example, you may look at the ball of radius r in this random metric. And using subadditivity, it's not very hard to show that when you take r bigger and bigger, you will converge to some deterministic shape. But now what is much harder is to ask the question of by how much your random metric fluctuates around the asymptotic shape. So in certain specific cases of last passage percolation, the answer is known and it's related to random matrices. But for example, in this case, it's far from being well understood. But somehow the techniques of this course about noise sensitivity, at present they give the best estimates on how much it fluctuates around the asymptotic shape. So this will be another application of these techniques. And just to finish this impressionistic view of the course, I'll say a few words about the main tools. So as I said already, first part of this course will be, at least this first lecture will be very simple. It will be concepts which come from computer science and which are quite old, and I will explain what they are and some theorems about these. Then in the second lecture, Jeff will introduce discrete Fourier analysis. And very quickly, so you know that if you take a periodic function, you can decompose it into Fourier series. And it turns out that if you take a Boolean function, you can do the same. There is a very natural theory of Fourier analysis on the hypercube. So exactly similarly as in the case of the circle, a Boolean function will be decomposed like that. And the spectrum of this Boolean function will exactly answer questions about being noise stable or noise sensitive. And somehow the noise stability regime will correspond to Boolean function whose spectrum will be concentrated on small frequencies, and noise sensitivity, which is at the opposite of the in the world of Boolean function, will correspond to function where all the spectrum is concentrated on high frequencies. So this will be the content of the next lecture. And now I give a few other tools, but this won't mean anything to you, but just so that you catch the name for later on. Another technique which will appear in the third lecture will be hypercontractivity, which is a quite well-known inequality in functional analysis, and it will imply a theorem that I will state today. Another technique which will be completely different is something called randomized algorithm. And very roughly speaking, if you take a Boolean function, and if you can find an algorithm which computes your Boolean function by looking at bits one at a time, and if it is such that you can compute the output of your function so that you look at very few bits, then we'll see that necessarily the Boolean function has to be of very high frequencies. So this will be a very simple criterion to prove that something is noise sensitive, namely to find a randomized algorithm which computes it in a small amount of time. And finally, if we have time, we'll explain how to prove sharp results about noise sensitivity by considering the frequencies of this Boolean function as random fractals of the plane. Okay, so now I'm done with the impressionistic view. So now I shall try to be rigorous. So yeah, I don't know how this works. But okay, so today it will be a chapter about Boolean function. And somehow I will try to state results, which will be, most of them will be proved later in the course, but these will be results which will concern Boolean functions in the very general case. So These are things which are very well known in computer science, but I believe that this is not as known in the probability community, and that some of these theorems are really of some interest. But let me start with let me recall the definition of Boolean function. So, as I said in the file, a Boolean function will be a function f from the hypercube into 0, 1, and sometimes into minus 1, 1. So these are just conventions, but sometimes it will be helpful to have something of expectation 0. Okay, so as I explained in the first half an hour, it will often be necessary to consider our inputs as random strings of bits. So usually we will endo the hypercube so we will often denote it like omega n, and we will endo it with the uniform measure P equals Pn, which you can write it like that. So of course, when you want to apply such techniques to, for example, percolation, you might be willing to consider other measures on your hypercube, and for example, the p-biased measure. So in the next lecture, Jeff will explain a few concepts in this greater generality, for example, Rousseau's formula that Vincent mentioned yesterday. But today we'll mostly stick to this case. I might sometimes mention things here, but we'll mostly stick to the uniform measure case. So let me give you a few very basic examples of Boolean function. So the first one is as follows. Take n bits and let the output be decided only by the first bit. So there's not so much content in this example. This is called dictatorship. Somehow, in terms of the definition I gave, this is extremely stable, but yeah. So I give the example because it will be an extreme Boolean function among all Boolean functions. So this is very simple, but it's good to keep in mind. Another one, which is extreme as well, is a very weird way of designing a voting scheme. It would be as follows. Take f of x1, xn to be the product of all the bits. So, well, this is particularly unstable because if anyone changes in mind, you change the output of the function. And this is called parity. Another example, I already gave it in the PDF file, would be the majority function. So here you take n to be odd, and you take f of x1, xn to be the sign of the simple random walk. Maybe to match with the Al Gore and Bush example, let me give an example of iterated majority. so iterated majority. So here let us take the number of bits n to be 3 to the k. And let me draw you the picture in the case k equals 2. So if k equals 2, we have 9 bits. And the Boolean function would work as follows. Group your 9 bits as 3 groups of 3. And look at your bits. For example, this. And now apply majority in each of these blocks. So this would give plus, this would give minus, and this would give minus. So this is like the k equals 2 layer. This would be the k equals 1. And the output of the Boolean function would be here minus. And if you want to iterate it more, for example, the layer behind this might come from something like this. And so on. So you see how this is not very important for the what follows, just an example of a Boolean function. You can find in the notes a fifth example, which maybe I'll come back to it at the end of the lecture if I have time, but since I won't need it at all today, I'll skip it. But let me just say that this is related to the random graphs of Erdős-Rényi. So somehow when you take a random graph and you wonder about a property of your random graph, for example, having a triangle in the random graph, you may think of it as a Boolean function whose inputs are the edges of the complete graph on n vertices. So this is another, this may create you another big family of Boolean functions. But the most important example for us will be the Boolean function in the case of percolation, namely the left-right crossings in percolation. So, so here you may take any shape. And if you prefer, we can take only rectangles, but this works for any shape. And you take two arcs on your boundary, and say you are on the triangular lattice, but it works as well on Z2. Take n to be large for the picture, and look at the rescaled. Say this T is the triangular lattice. You look at the rescaled triangular lattice in this grid. Of mesh 1 over n, and take any approximation of your domain with hexagons, and look at the Boolean function, which will, as in the slides that I had before, will tell you that this is 1 if you have some open path from left to right. Okay, so maybe this should be up. So Fn of omega will be 1 if there is a left to right, and 0 if there is a dual path coming from the top to the bottom. So here omega is an element of the hypercube, which depends on all the bits inside this picture. So you have about n squared bits. Okay, so well, on all these examples, you see that this one will be useful in the exercise sessions and things like this to start working a bit with Boolean function, because it has a an iterative structure which makes it easier to work with. But really the main goal will be to apply general theorems on this kind of picture where we don't know how to handle it directly for now. So now I will, so I'm done with the examples, and I will introduce two concepts which are related, which are the concept of pivotality and of influence. So pivotality and influence. So in what follows, we'll take, we'll fix a Boolean function f, Boolean function f. So again, either in this or in this. And I'll define all the notions that we will need for this Boolean function. So the first notion is the notion of a pivotal point. So Vincent defined it in the case of percolation yesterday, and it's easy to extend it to any Boolean function as follows. So the variable or the bits I in n. So this denotes the set of the bits is pivotal for omega if f taken omega is on omega is different from f of omega I, where omega I is equal to omega except the ith bit is flipped. So this is a very simple notion. For a Boolean function f, so this is a random notion, but the variable I will be pivotal if when you switch its value, you change the output of the function. So a related notion is the notion of the pivotal set. P which depends on omega, and implicitly also on the Boolean function f. This is just the set of all the variables which are pivotal. Okay? So now let's see what it gives in one or two examples. So if you take, for example, majority, so we've seen that majority on n bits is related to the simple random walk. So like that. So if n is odd, at time n, you can end up in 1, 3, 5, or -1, and so on. So if you end up in, for example, 5, then it's easy to see that the pivotal set for this configuration omega is basically the empty set. Why that? Because if you flip anything here, you will just change by 2 the final value, but you won't change the sign. So in the case of the majority function, very often the pivotal set of majority is empty, and sometimes when you happen to be equal to 1 or minus 1, then about half of the bits will be pivotal. So why half is just because, say you end up being here, then all the bits wait.
All the bits where you move up are pivotal, and that's approximately half.
Yeah, okay. Yeah. So, okay, so the case of the majority function, the pivotal set is most of the time empty, and with probability about 1 over square root of n, it will take half of the bits. So this is not the most interesting case, but in the case of percolation, Vincent has drawn already some pictures yesterday. So if we take percolation, the left to right crossing in a rectangle, so remember that Vincent drawn this picture that if you take a bit, so in our case this would be a variable, right, an edge. For this edge to be pivotal, you need to have an open path coming to this point and an open path coming like that. And you need to have a dual path, so like this. So white will be dual in this picture, connecting the top to the bottom. So if the configuration omega outside of the edge E is like this, then your edge is pivotal. So now, what is the pivotal set? Well, as Vincent said, in Keston's argument, he uses the fact that the pivotal set is rather large, at least logarithmically large. And why is that? Because you have many other regions like that with the same 4 arms picture. And so on. So when you do have pivotal points, usually the set of if you just want to draw the pivotal set, you'll end up having some, seen from far away, some kind of a fractal subset of the square like this. And I think Hugo in the TA sessions maybe prove that this set is, with positive probability, very large. Yeah? No? We won't need it today, but yeah. So just a side remark, in the same fashion as here, sometimes the pivotal set is empty. In the case of percolation, it might be that by Russo-Seymour-Welch, it might be that you have 2 disjoint open paths from left to right, and in that case, necessarily the pivotal set is completely empty. Okay, so the pivotal set in the case of percolation has a very rich structure with positive probability. It has a fractal looking like this, and sometimes it's just empty. Okay, so now I'll move to the notion of influence, which is more or less the same thing as pivotality, just quantifies what is the probability for a point to be pivotal. So the influence, so I still have my Boolean function that I fixed at the beginning. The influence of the ith variable is, we'll denote it by like this, I of f. And this is, by definition, the probability that the point I is pivotal. And this is also the probability, this is the same thing, that f of omega is different from f of omega I. So, in these lectures, we will see that if you take a Boolean function, if I don't tell you what the Boolean function is, but I tell you the information about all the influences of the bits, somehow it already provides you with a lot of information about the Boolean function. So, therefore, we define the influence vector of f to be the vector which gives you the information about all the individual influence. And we'll denote it by inf of f. So, another notion that we will need a lot in this course is the notion of total influence. So what is it? The total influence of f is just defined as the sum of the individual influences, or if you prefer, this will be the L1 norm of this influence vector. And somehow we've seen yesterday that this quantity encodes something about what Vincent called sharp threshold. In the following sense, if you take a function f on the hypercube, which is increasing, which is monotone, in the sense that f of x is less than f of y, where x and y are strings of bits, and there is the obvious ordering between these two, then the expected value of f under the p-biased measure is, of course, an increasing function, right? So yesterday, this was the particular case where f was the left-to-right crossing event, and when you increase p, it's more and more likely that you cross. So if you draw this function, you'll have some increasing function like that. And so now, at least at p equals 1/2, Jeff will extend these things to other values of p. The derivative of this function is exactly given by the total influence. So this is what Vincent called the Rousseau's formula. So this will be proved in the lecture tomorrow by Jeff. So the total influence and this influence vector already encodes properties of this type here. Okay? So all of this was pretty formal. Not much content in this, but now I'd like to start introducing one of the main statements of this first lecture. But before, I'd like to motivate it a little bit. So this will be about, it's called Kkl Theorem. So now that we define all this business, when you take any Boolean function, you might ask the question, how influential how influential can the variable well, I'm not sure this is proper English, but okay. So maybe to give just a concrete example, how could we rephrase this notion of influence? Say you have a voting scheme with Boolean function f, and say you have n people voting and you are the ith voter, and imagine everyone voted according to the uniform measure and you arrived late. So everyone voted, it's already on the blackboard and people started computing the outcome. You come there and you're like, oh, sorry, I'm late. And you see on the blackboard that there is the missing box for you. Most likely, it will be very boring for you because it won't make any difference. But maybe everyone will look at you like you're the swing voter. So the influence is exactly the probability that in this context you would just by yourself make the flip. So maybe you would like to design a Boolean function which makes this scenario less likely as possible. Maybe, the first question was a bit vague, but can you design a Boolean function such that all its influences are very small? So before the Kkl theorem, there was a first inequality which is well known, and which is the following. So if you take f a Boolean function, or n2 minus 1, 1, then the variance of f is always bounded from above by the sum of the influences. So if you want, this is bounded by above, but what I defined before to be the total influence. So this is known as a Poincaré's inequality. Because somehow influences are about discrete derivative function, and this reminds you maybe of inequalities like integral over Rn of f squared times the Gaussian measure is less than some constant which depends on n times the L2 norm of the gradient, which are the classical Poincaré. So in this discrete setting, this inequality, which is simple to prove and will be done in the exercise sessions, this already provides you with a partial answer to this question here, right? Because of this inequality, when you take any Boolean function f, there has to be at least one variable I whose influence is bigger than the variance of f divided by n. Okay, so if you take a voting scheme which is well balanced, meaning that half of the time it will take value 1, half of the time value 0, somehow you can't design a Boolean function which will do better than this 1 over n here.
This is
Yeah, good question. So this would be also true for the p-biased measures. I'm not 100% positive. Sometimes there are p constant. Well, okay, I don't know. But here, here I state it only for p equals 1/2. No, I think for p-biased you would have the same, but you just need to define the influence accordingly with the p-biased. Okay, so now the natural question is, does the Poincaré inequality provide you with the right intuition, or can you, I mean, can you actually design a Boolean function which match with this or not? So before answering, maybe let's think of Boolean functions which have low influence. So parity and dictatorship, this doesn't work because you can check the influences are all equal to 1. Let's look at the majority. Majority function. What is the influence of a variable in the majority function? Well, we've already more or less said it before, but if you want a variable to have an influence on the outcome, you need your simple random walk to be either equal to 1 or to -1 at time n. Okay, so an easy exercise is to find that for any variable I, the influence of this variable on the majority on n bits, as n goes to infinity, this behaves like a constant divided by square root of n. So this shows that you can design Boolean functions with rather small influences, but this is still very far from the bound achieved with Poincaré's inequality. So now let me state this Kkl theorem, which improves on this. So Kkl theorem. So there exists, so this is from 88. There exists a universal constant C such that for any Boolean function, there is at least one variable whose influence is greater, almost the same, what gives the Poincaré inequality, but improved by a factor of log n. Okay, so you can do much better than what you do with majority function, but this doesn't tell you yet whether this is sharp or anything. This just improves with a log n factor. So maybe the first time you see it, you may think, well, gaining a log n factor, that doesn't seem to be very strong yet. There must be some exponent or something like that. But it turns out that this is not the case. So let me state two reasons why this theorem is, I believe, very interesting. So the first reason is that it is sharp. So it indeed improves on the Poincaré's inequality only by a log n factor, and it turns out that you can design Boolean functions which whose influences are of this order here. So this is a, so let me give you such an example. So this is called tribes. So you take n bits, and you divide these n bits into packets of size, into packets of equal size, a little bit like iterated majority before. But now what you do is that if you can find one of these blocks where all the bits in these blocks are pluses, then you set your Boolean function to be 1, and else you set it to be equal to 0. So now the only thing we need to do to fix this Boolean function is we need to fix the size of each of the blocks. And preferably we'd like to fix the size so that the variance is not going to 0. And computation shows that this is achieved by, as a function of n, as log 2 of n minus log 2 of n. So I don't exactly know how they came up with such an example, but this shows you that this Kkl theorem is sharp. So, well, it doesn't show you, but in the exercise sessions, you'll prove this. So now a second reason. Let us look at the following particular case of Kkl theorem. Let's say you take a Boolean function f, and let's say this is monotone, and let's suppose that all its influences are the same. So every variable has the same probability to switch the outcome. So by the Kkl theorem, this implies that, and Rousseau formula, the derivative at p equals 1/2 of the probability that f equals 1, EP of f. Rousseau's formula, which will be proved tomorrow, tells you that this is the total influence. And if here we assume that all influences are the same, so in particular they have to be bigger than that. So in particular here we get that this is bigger than n times a certain constant variance over f and log n. So you get that this is bigger than and so now even if Kkl theorem doesn't improve so much on the classical Poincaré's inequality, if you would use Poincaré's inequality here, you would get something which would not go to infinity. Well, here what you get is that it's a very natural assumption. You take some, I don't know, voting scheme, all the influences are the same. Necessarily, when you move the bias p, and if your variance is reasonably bounded, what we're proving here, we're using the Kkl, is that necessarily the threshold near p equals 1/2 has to be sharp. So this Kkl result is completely general. We assume very little on the Boolean function, and we get this log n derivative. And if you remember Vincent's lecture yesterday, case an argument using Rousseau-Seymour-Welch at many scales and so on, gave this log n at p equals 1/2. But here we're not using any Rousseau-Seymour-Welch or anything like this. It's just completely, somehow this is the magic of this Kkl theorem. So, let me give a second So in their paper in 88, they gave several results. Let me give you a second one. So maybe Kkl2, which says the following, that there exists a universal constant C such that the total influence, which I remind you is the sum of the influences, is always bigger than C times the variance of F times log 1 over delta, where delta is the maximum influence. So let me rewrite it like that. Recall that I mentioned before that in the set of all the individual influences encode a lot of information on the Boolean function, and we introduce this influence vector. So we can rewrite this inequality as the L1 norm of the influence vector is greater than C times the variance of F times log 1 over the L infinity norm of this influence vector. So it might not seem very useful to all the time use these LP norms on the influence vector, but we'll see that it will be useful to play later with LP norms of this influence vector. Here the L1 norm and the L infinity norm, they interact together in a non-trivial way. Why? Because so now if you wanted to make the total influence very small, if you wanted to have a Boolean function which has a derivative very small, you might say, let's try to make each individual influences very small, right? That seems reasonable because you sum them all. But what this tells you is that in this discrete world of Boolean functions where you have many restrictions of the combinatorial type, this is not so simple, because if you push all the influences to be very small, in fact, you actually, when you sum them all, you get something large. So you need to compensate one way or the other. So that's what this inequality tells you, and this can be used to prove PC equals 1/2 in a similar way as what Vincent did yesterday. Okay, so you can read of a third Kkl theorem in the lecture's notes, but I will skip this one. And now I'll move to noise sensitivity. So first of all, I should define what is this omega epsilon that I used many times in the PDF file at the beginning. So in what follows, epsilon will usually be considered as a fixed parameter which won't depend on the number of bits n. And if you take omega, a random string of bits in the hypercube, sampled according to the uniform measure. How do you produce omega epsilon? Well, let's take omega epsilon to be y1, yn, where for each I, yi equals xi with probability 1 minus epsilon, independently of each, for each bit. And with probability epsilon, what do? Maybe the most natural would be to just flip it. Somehow it will be more convenient in these lectures to resample it. So what you do with probability 1 minus epsilon, you keep the site the same as it is. And with probability epsilon, you take it to be 1 with probability 1 half, minus 1 with probability 1 half. So if you think about it, it's almost the same as just flipping the bit with probability epsilon, but you need to change epsilon into epsilon over 2, or 2 epsilon, I don't know. But this is just the same thing, but this will avoid us to have many factors of 2. So it indeed corresponds to, if epsilon is small, it indeed corresponds to a slight perturbation, because you only resample a fraction epsilon of the bit. So now, let me introduce the definition of noise sensitivity. It might appear maybe a bit strange at the beginning, but okay, so definition. What might appear a bit strange is that when I said in the PDF file that noise sensitivity corresponds to having a covariance going to 0, either we would quantify what it means, or we need to have a notion which is for a sequence of Boolean function. So let me take a sequence of Boolean function. So we will say that the sequence is noise sensitive. So this sequence of Boolean functions is noise sensitive if and only if the covariance of Fn of omega with Fn of omega epsilon goes to 0 as n goes to infinity. So this will be when we take, for example, left to right crossings in percolation. They are indexed by the size of your rectangle, for example, and you let the size go to infinity. And being noise sensitive, oh, sorry, there's something missing here. You want this to hold for any fixed value of epsilon. So using Fourier analysis, we'll see that if it holds for one value of epsilon, it actually holds for all. So this says that whatever small amount of perturbation you put, when you start having a large-scale event, or when you go to n goes to infinity, you decorrelate more and more. So I'll stop a second on an equivalent definition of noise sensitivity, which might appear slightly stronger. Because what this says here is that somehow asymptotically, the random variables Fn of omega and Fn of omega epsilon are more and more independent, right? In fact, noise sensitivity says a little bit more. It turns out that asymptotically, Fn of omega epsilon and omega are getting independent. So what does it mean? It means that if you take that was better. If you take a sequence Fn, we have the following proposition, and this will be proved in an exercise session later with Fourier analysis. If the sequence Fn is supposed to be noise sensitive, in this sense, then the following three facts hold. You get that the expectation of Fn of omega epsilon knowing omega minus the expected value of Fn goes to 0 in probability. Since the perturbation is symmetric from omega to epsilon and backward, you also get this. E of Fn goes to 0. And another way to write all of these things is to say that the variance of the conditional expectation goes to 0. So now let us see what it means. So for example, if we take this statement here, to get some intuition, remember the case of voting schemes. Imagine you have n people, and you have for each n you have the voting scheme f of n, and you do your election, but somehow what you collect is only the omega epsilon, right? Because some errors has been produced, and you'd like to know what information, knowing all the actual configuration that you receive, what is the information preserved about the actual outcome that you'd like. Well, this statement here, or this one here, tells you that if your voting scheme is noise sensitive, basically nothing remains. All the information has disappeared. So in the percolation, if I take, if I know all the edges in a big box, and I tell you that only a small portion has been resampled, I have no clue how the clusters looked before. The whole thing has vanished somehow. And while it's not, without Fourier analysis, it's not completely clear how to go from left to right, but to me, this seems stronger because this probably gives you much more information than if you only knew Fn of omega epsilon. So, okay, so this is what noise sensitivity is. So of course, it's not quantitative at all. It's almost like you're taking Markov chains and you're saying, okay, I can prove that there is a limiting measure, it equilibrates, I don't know. Later on in the course, we'll need to have something much more quantitative, namely how much is percolation sensitive to noise, like at what speed that this goes to 0, that kind of things. Like we'd like to understand better the sensitivity of the percolation picture. So in the last minutes, in the last 5 minutes, I'd like to give a theorem which was proved by Benjamini. Oh, I didn't say what Kkl stands for. It was can, Kalai, and lineal. Sorry. And now I will state a theorem by Benjamini, Kalai, and Schramm. So I call it BKS theorem. This is from 98. And so now they found a very simple criterion to prove that a sequence of Boolean functions is asymptotically noise sensitive. And if you go to the exercise sessions, you'll see that sometimes to actually prove that the disk covariance goes to 0, if the Boolean function is complicated enough, it can be very non-trivial. So for example, if Fn is the left to right crossing in percolation, Benjamin, Nikolai, and Schramm, they had to go to this sort of general setup to be able to answer this question. They couldn't do it playing with pivotals or with Rusesem Welch or things like this. They sort of had to go through the Fourier picture. So let me state their criterion. So if you take Fn, a sequence of Boolean function, they show that it is noise sensitive if and only if the sum of the influences squared goes to 0 as n goes to infinity. So maybe to make it slightly more general, our sequence of Boolean function, it might be defined on a number of bits which is not equal to n. And why do I use this? It's just because in percolation, the Fn left to right crossing, it involves in fact roughly n squared bits. So in general, the definition, you don't need to have, well, you may have much more bits at the nth level. So here, we just want that the sum over all the bits of the influence squared goes to 0. So what Benjamin, Nikolai, and Schramm theorem tells you is if you take a sequence of Boolean function in such a way that the influences are small in this sense, then necessarily your sequence is noise sensitive. Necessarily it has to behave in a chaotic way if you perturb just a little bit your string of bits. So when I said that we, in this course, we'll play around a little bit like in analysis with LP norms of influences, you can see in this theorem that I already mentioned results involving the L1 norm of the influence vector, which was the total influence, the sharp threshold, the L infinity norm, which was, there was a balance between the L infinity and the L1 norm. This thing is again something about the L2 norm squared of the influence vector. If you know that this goes to 0, you know that you are noise sensitive. So let me just finish with the example of majority. So this is easily seen to be noise stable. Just a second, I'll give the definition of noise stability here. The opposite situation, noise stability, is when you have the probability the sup over n of the probability that Fn of omega is different from Fn of omega epsilon. You want this to go to 0 when epsilon goes to 0. So when the noise gets really small, you want that the outcome of the election is not, well, it's perturbed very little. Okay, so majority, it's not hard to show that this satisfies this criterion when n goes to infinity. And so we'd like majority to not satisfy this criterion, of course, right? So let's just check, and I'll finish on this. We call that if you have the majority on n bits, we've seen that the influences was something like c over square root of n. So now if you apply the BKS criterion, you see that well, it doesn't go to 0. And yeah, so later in the course we will study influences of percolation, like in the Vincent picture. So influences was the probability that this event would occur, and using techniques from percolation, one can see that. But to take care of the boundary behavior, it's not completely trivial, but we can see that indeed this criterion goes to 0, and that's how they prove that indeed the percolation picture is noise sensitive. So a first part will be first to prove these kind of results, and what we will do is we will start by the Kkl theorem, because it's interesting in itself, and somehow the proof of the Kkl theorem is very close in spirit to this proof here. And later we'll analyze more closely the set of influences, and we'll have a first proof of noise sensitivity of percolation. And then we'll see other approaches that I mentioned very quickly with randomized algorithms and things like that, but later in the course. Okay, so I'll stop here. Sorry.
F is 0 seems to be a problem. Totally balanced doesn't mean don't answer my problem.
Sorry?
If you take F equals 0 and not 0, then all that sum is 0. But
If I take f equals 0, you say?
Yeah, well, that's not very noise sensitive.
That's true, but somehow it satisfies the criterion on the right. So somehow, that's a good point. Like the definition is, well, what used to be the definition of noise sensitivity here. It's slightly meaningless if your sequence of Boolean function has variance going to 0. But we include it here. So if f is identically equal to 0, this would be called noise sensitive, but this yeah, maybe one could normalize. Classically, that's what is done in the, well, the literature is not huge, but if you restrict to sequence of Boolean functions whose variance is bounded away from 0, then you get something intuitively very meaningful. Okay? Sorry, does it imply what? I don't, this is not something like constant what? Later, okay. But this has changed to noise stability here. I don't know if you... Okay.